So if we want to integrate x over the fourth root of x plus 2, anybody have a suggestion on what we should do first?
Set u to x plus 2.
Okay. So yeah, we're going to set u equal to x plus 2. The reason we got to do a u substitution is if we look at this, first of all, it's a quotient of two different functions. So therefore, we can't just straight up use the power rule on any of it. And another reason we can't do that is because we have a function x plus 2 within another function, the fourth root function. So there's a composition of functions, which makes things even more complicated. And there's no just simple rule for x over the fourth root of something. So it's got to be reworked somehow into a u sub. So if u is x plus 2, conveniently du is just
dx.
dx. And then we're going to have to do something with that x, which means we're going to have to manipulate this into x equals u minus 2. And so if x is u minus 2, this integral becomes u minus 2 du over u to the 1/4 or the fourth root of u. Everybody good with that so far? Yes, no, maybe?
Yeah, good.
All right, cool. So from there, the next thing we need to do is think about what I told you about these functions where I have like a binomial or a trinomial or some polynomial in the numerator, and then just a singular term in the denominator. Whenever we have that, we just want to divide term by term each thing. So u to the first divided by u to the 1/4 should be u to the 3/4, subtract the exponents, right? And then a minus 2 divided by u to the 1/4 ought to be a minus 2u to the negative 1/4 power. And now we've got this set up so that we can use which rule?
The reverse power rule.
Yeah, we're just going to use the power rule in reverse. Perfect. So we'll just do that. U to the 3/4 will go up to become u to the 7/4. And when we divide by 7/4, that'll be a 4/7 out front. And then u to the negative 1/4 will go up to 3/4, and we'll divide by 3/4. So that'll be like multiplying by 4/3. So we'll get minus 8/3 u to the 3/4. Plus, always plus a constant. Don't forget the plus a constant. And then we just substitute back in our u, which was x plus 2. So we got 4/7 x plus 2 to the 7/4 minus 8/3 x plus 2 to the 3/4 plus our constant. Get it or no?
Good.
Cool. No questions, no issues there. Everyone's okay with that. Everybody feels all right about that. Okay. Any other questions from any of the homework problems?
Yeah, actually, could you show the one right before as well? The 1w.
Sure, what's that one?
Integral of x times root x minus 1 dx.
So same thing here. We're going to have to do a u substitution because we have a function x times another function root x minus 1. And there's no way to distribute this through here nicely to make it work out with the power rule. And so we'll have to do a u sub to try to get it rearranged so that we can use the power rule. So if we let u equal what's inside the square root, x minus 1, then just like the one before, du should be just dx. And in this case, x should be u plus 1. And so we should be able to go in now and replace the x with a u plus 1. And then the x minus 1 with a u. And square root of u is the same as u to the 1/2. And we'll replace the dx with a du. Good or no?
Oh, Yeah, that makes sense.
Okay. And so now it's still a function times another function, but now both of those functions can easily be distributed together because I have the square root around a single term. So u to the first times u to the 1/2 is u to the 3/2, and u to the first times 1 is just u to the 1/2 du. Now we integrate with the power rule. So 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus our constant, and then we just substitute our x minus 1 back in for u. 2/5 times x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. Good or no?
Yeah, that makes sense. Thank you.
Mm-hmm. Other questions?
How did you know that du was equal to dx?
The derivative of u is du, and the derivative of x minus 1 is dx. The derivative of x is dx, and the derivative of minus 1 is 0.
Oh, right. Okay.
Does that make sense?
Yeah.
Okay, cool. Other questions from the homework?
Actually, could you show 2f as well?
2f, sure. What is 2f?
Integral with the what's called the lower limit of pi over 4, and then the upper pi over 3, and then secant theta and tangent theta, then with d theta.
Just secant theta, tangent theta?
Yeah.
Okay. So secant theta, tangent theta is one of the rules off of the integral rule sheet that's posted in the Google Drive. So the integral of secant theta, tangent theta is just secant theta.
Yeah.
So this should just become secant theta. And we'll then evaluate it from pi over 4, our lower limit, to pi over 3, our upper limit, which means just plug those in. Secant of pi over 3 minus secant of pi over 4. And the secant of pi over 3, that's the reciprocal of cosine, right? Cosine of pi over 3 is 1/2. So the secant of pi over 3 is 2. And then this one, cosine of pi over 4 is root 2 over 2. So the reciprocal of that is 2 over root 2. 2 over, I'll just write it that way, 2 over root 2. That's also equivalent to just root 2. So this is 2 minus root 2.
Thank you.
Mm-hmm. Other questions?
Can you do 1y?
Sure. What was 1y?
The integral of x squared over the square root of 1 minus x dx.
All right. So another u substitution one. I don't have a single term in the denominator, so I can't just divide everything. So I have to substitute that out so that it will be a single term in there that I can divide everything by. So we'll let u equal everything inside the square root, 1 minus x. And then du will be, the derivative of 1 is 0, but the derivative of negative x is negative dx. So du will be negative dx. And we're also going to need to figure out about x squared, right? And so we should be able to see that x is equal to 1 minus u. So that'll give us x squared is just 1 minus u squared. So far, good?
Yeah, that's the only part I needed help with.
Okay. Anybody want me to finish that one off, or? Yes, no, maybe?
Yes.
Yeah.
Yeah, okay. All right, we'll finish off. So we're gonna multiply by a -1 on the inside to give us our negative dx, which means we put a negative on the outside. So we'll have negative integral x squared, which is gonna be 1 minus u squared. The negative dx will become our du. And in the denominator, we'll have root u. And so now we have a negative integral. We'll have to distribute out the numerator, 1 minus 2u plus u squared over u to the 1/2 du. And from there, now we have a singular term in the denominator, so we can just divide everything. And if we want to distribute that negative sign through now, so we don't have to worry about it later, we can. I'll probably just do that. So -1 divided by u to the 1/2 is negative u to the negative 1/2. And then -2 is going to give me a 2, right? 2u over u to the 1/2 ought to be 2u to the positive 1/2, right? Of u to the first over u to the 1/2. And then this is a negative u squared over u to the 1/2, so that'll be minus u to the 3/2 du. And so now we're ready to integrate. Everybody good to that point?
Yeah.
Okay. U to the negative 1/2 will go up to u to the 1/2, and we'll divide by 1/2, which is multiplying by 2. So we get -2 u to the 1/2. This one will go up to 3/2 and multiply by 2/3, so plus 4/3 u to the 3/2. And then this one will go up to 5/2 and we'll divide by 5/2, so minus 2/5 u to the 5/2 plus the constant. And then you just go back in and replace. So -2 times 1 minus x to the 1/2 plus 4/3 1 minus x to the 3/2 minus 2/5 1 minus x to the 5/2 plus a constant. Good or no? Any other questions?
Are you going to post the answer key to this worksheet before tomorrow's quiz?
Yeah, I'll have it up. I'll put it up right after class today.
Okay, thank you.
Mm-hmm. No other specific questions from that? All right. In that case, we will move on to what we're going to talk about today, which will still give us a little bit of practice with integrals because we're still going to be dealing with integrals for the remainder of the year. But specifically, we're going to be dealing with finding the average value of a function on an interval. So if you think way back, remember yesterday we were thinking way back to the ancient Greeks. Remember that? And I was like, think about the ancient Greeks. Did I tell you guys to think about the ancient Greeks? Remember that?
Yeah, you told us to think about the ancient Greeks.
Yes, and then you finally figured out Pythagoras. Well, today you're going to think about your own life, and you're like, you're going to think back to first or second grade when they taught you how to find the average of a bunch of numbers. Maybe kindergarten, I don't know, something when life was easier. And they said, all right, we're going to find the average of 7 and 11 and 14. And what did you do? You added the 3 numbers together, right? And then you divided by 3. And you found the mean or the average. And they were like, look at how exciting that is. That's the average. We could use that to find, the average age of all of the students in our class. And they probably added if you were in first grade, they probably were like, I'm 5, I'm 6, I'm 7. And they added a bunch of different kids together and divided by the number and said, oh my gosh, the average is 5.2 or something like that, or 6.1, and you got an average age of all the kids in the class. You do something like that? Maybe?
Yeah.
Yeah, you all know how to find an average. Well, that's all real great, finding an average of a bunch of numbers. That's easy to do. You add them up, you divide by the number of them. But what if I wanted to know the average value of a function, of a continuous function on some interval? So suppose I said that the depth of a swimming pool varied throughout the year, and I knew that it followed some continuous function that looked like this. Let's say at the beginning of the year there was some water in it, and it was, started to warm up, and so some water evaporated, and then it got closer to fall and it started raining, and so the amount of water went up in the swimming pool or in some pool of water, right? The depth might decrease and then increase. And then maybe I have some function that represents that. Well, if I just asked you to find the average depth of the pool during the entire year, the only way currently that you'd have to do it is just take some points, like, oh, I measured it on January 1st, it was this depth. I measured it February 1st, I measured it March 1st, April 1st, May, and so on, right? You find a bunch of data points, and what would you do with each of those data points? You'd add them all together, and you'd divide by hopefully 12 for the 12 months. Or you might do it, 365 of them, right? With 365 days in the year, you might have done 365 data points, add them all together, divided by 365. True? That sound like what you would do?
Yeah.
Yeah. I mean, that's how you were taught to find an average. Well, that value is not actually correct if you have a continuous function where it's varying between those data points. And the more data points you have, the better the average is. But if we could include every single value on this continuous function, rather than just a set number of data points, that should give us a true average if we could include an infinite number of those data points, wouldn't it? If we knew at every instant in time for the entire year what the depth of that pool was, we should be able to find the average depth. True? That's our hope. Right? It seems like it's reasonable that we should be able to. If I know every data point, I should be able to add them all up and divide by the number of them there are. True?
Yeah.
Yeah. So it becomes a problem, though, when there are an infinite number of data points on some sort of closed interval, right? There are an infinite number of points between A and B, aren't there? There are. There are an infinite number of points between A and B on this function that I've drawn over here. And so since there are an infinite number of points, in order to sum together an infinite number of those data points, we need to use an integral. And so that's what we're going to do to try to find the average value of a continuous function on an interval. What we want to do is we want to find a height at which the area underneath a straight line made at that h value, at that height, gives us an area that is equivalent to the area underneath the curve from A to B. So if I make a rectangle from A to B that goes up to h, the area of that rectangle in red needs to be exactly the same as the area underneath my curve from A to B. And if I can make this area the same as this area, if I can make the blue and the red areas equal, that tells me that the average value of my function is h. That h would be the average value of that function. So that's what we want to do, is we want to use just a little bit of calculus to make h our average function or our average value of the function, and we want to go to solve for h. Does that make sense?
Yep.
Cool. So first off, what's the area of this blue thing if this is the function f of x? This is the easiest question so far this unit. What's the area underneath f of x from a to b? It should be what? Sorry, there's a loud plane from Miramar going over.
It's the integral of f of x dx from a to b.
Exactly. It's just the integral of f of x from a to b. That's all it is, right? That's what that blue area is. Well, we want that to be equal to this red area. What's the red area?
P minus a times h.
Right, it's just a rectangle. It's just the length times the width or times the height, b minus a times h. And so if we are looking for h ought to equal our average value, and it ought to be this integral divided by b minus a. Or sometimes usually we write it as 1 over b minus a times the integral from a to b of f of x dx. And this is what we call the mean value theorem for integrals, or the average value theorem for integrals. Okay. This will always tell you the average value of the function f of x between a and b. Good or no? Everybody good with how we developed that?
Yeah.
Cool. All right, so let's see if we can use this for a continuous function like f of x equals 4 minus x squared. We want to find the average value of this parabola, the parabola 4 minus x squared, and we want to figure out if our function actually hits that average value somewhere on the interval between a and b. So what do you think we should do first? What do you think we should do first?
Find out if f is continuous or not.
Yeah, is f continuous on our interval?
Yes, because it's
Because it's what?
It's a polynomial.
It's a polynomial. Okay, so good. We've done the first part. We've shown that it's continuous on our interval. Then the next thing we need to do is just set up that equation that we just wrote. The average value, h, ought to be 1 over b minus a times the integral from a to b of the function. Easy enough?
Yes.
Great. So that gives us 1/3. What's the integral of 4 minus x squared?
four x minus 3x over 3, or 3x cubed over 3.
Okay. From 0 to 3. And now we'll just evaluate this. It's now 1/3 of 12 minus 27/3, which is 9. Minus, this is 0 minus 0 inside of there. If I plug in 0, we get 1/3 of 3, which is 1. So the average value of 4 minus x squared between 0 and 3 is 1. And we want to know, does our function actually take on this value at some point? So all we'll do is set 4 minus x squared equal to 1 and get x squared equals what? What does x squared equal?
5. No, sorry.
Should be
3.
should be 3, which gives us x equals plus or minus root 3. And which one of those is on our interval between 0 and 3? Just
It's for 3.
Yep. So the average value is 1, and it occurs at the point square root of 3, comma 1. Good or no?
Good.
All right. Wonderful. Let's do another one. Why don't you guys try and do this one on your own? Yeah? Yeah. All right. I'll give you 2 to 3 minutes to see if you guys can find the average value of 1 over x between e and 2e. Ready, go. All right, so if we want to find the average value, it should be 1 over b minus a times the integral from a to b of our function. Right? Simple setup. 2e minus e is just e, right? 1 over e. And then what's the integral of 1 over x?
Natural log of the absolute value of x.
Natural log absolute value of x from e to 2e. And so this becomes 1 over e times the natural log of 2e minus the natural log of e. And what's the natural log of 2e?
Is it the natural log of 2 plus 1?
Yep, it's the natural log of 2 plus 1, right? Natural log of 2e, that's 2 times e, so you can do natural log of 2 plus natural log of e. And the natural log of e is 1. And then we have minus natural log of e, which is another 1. So we end up with natural log of 2 over e. That would be the average value. And if we want to know when does our function hit that value, we just set that equal to our function and get x equals e over ln 2. So this is our average value. And then it occurs at this. Good or no? Good, not good, maybe good?
Mostly good.
Good. Mostly good. All right.
Good.
Any specific questions on that or no?
So will most questions ask us what values like it hits?
Does it say that again? Oh, what value it I don't know. I wouldn't say most. It's possible that it could ask you that. Most of them probably will not ask you where it occurs, but it's possible that they could. So that's why I always just throw it on here, at least for these ones I did. Did I answer your question? You kind of cut out as you were answering or asking.
Yeah.
Okay. Just want to make sure. Cool. All right. Let's take a look here at this one. So suppose we measured the temperature every hour from noon until midnight and recorded all of our values in a table. And we wanted to know the average temperature during the 12-hour period. So in order to figure that out, if you were back in second grade, you'd just add them all up and divide by the number of data points. But now we know that temperature doesn't just go directly from 63 at noon to immediately become 65 at 1 and then immediately become 66 at 2, right? We know that each of those time periods, the temperature is maybe fluctuating up a little, maybe fluctuating down a little, and has some sort of smooth continuous, curve in between those values, right? Between noon and midnight. Would we agree this is a continuous function? Yep, this should be a continuous function. So if we want to find the average temperature of a continuous function, we need to do 1 over the ending value, b, minus the starting value, 0, times the integral from 0 to 12 of our function. We'll call it capital T of x. True? Everyone would agree with that? I hope. Yes, no, maybe?
Yeah.
Okay, cool. So since we don't actually know a function for capital T of x, we have to approximate that integral. The problem specifically tells us to approximate it using the trapezoidal rule. So if we're going to use the trapezoidal rule to approximate it, we'll still have a 1/12 out in front. And now we're also going to have a b minus a over n, right, over 2. So that'd be 12 minus 0 over 12, b minus a over n, divided by 2. So what are we really going to have out in front of that? Should have a 1/4 out in front of the whole thing. Yeah?
Yeah.
Yep, hopefully so. All right. And then we'll have 63, and we'll have 2 times 65, and 2 times 66, and so on, 2 times 58, and then at the very end, just a singular 55. And what does that come out to be? I'll let you punch that all into your calculator and see what you get.
Wait, I'm confused on where the 1/2 came from in front of the.
Oh, sorry, that's not a 1/2, that's a 1/12. Sorry. I just missed my 1 on the 1/12.
Okay, thank you.
Yep. I don't know how I missed that 1, but apparently I did. Anybody got an answer there or no?
65.166.
65 point what?
0.167.
167. Cool. Anybody else get that same thing?
Yep.
Cool. All right. Sounds good to me. Good or no? Any issues there?
Okay.
All right. Okay. So we're going to move on to something slightly different than this now, but still involving integrals. We're going to talk about something called an accumulator function. The name of that is not, super important there. But an accumulator function is one where we are looking at a rate of something, and then from that rate, we're going to integrate to get an actual value of something that is accumulated over time. So in this particular problem, we're going to be looking at how many potatoes were consumed during some certain amount of time. Okay. So between the beginning of 1972 and the end of 1973. And so we'll note that this function is a rate, C of t 2.2 plus 1.1 to the t power millions of bushels per year. So anytime we integrate a rate function, it will give us a number of something. Right, so suppose we're integrating the rate of millions of bushels per year. The integral of that rate will be millions of bushels. If we integrate gallons per hour, we should get gallons. If we integrate miles per hour, we should get miles traveled, and so on. So if we want to figure out how many bushels of potatoes were consumed, given this rate 2.2 plus 1.1 to the t power millions per year, all we need to do is write this out as an integral, 2.2 plus 1.1 to the t dt, and then figure out the appropriate limits of integration. Does that make sense? Or no?
Yeah.
All right, cool. So what is our limit going to be on the bottom? If 0 is the beginning of 70, what would the beginning of 72 be?
Two.
Should be 2. And what should the end of 73 be?
3.
The end of 73 would be the same as the beginning of 74, right?
4.
Oh.
So it should be 4. And so this is an integral. We could calculate this integral probably, but it's going to be easier for us if we use our calculator to do this. And so right now I'm going to teach you how you will use your calculator to integrate this. Sound good? Good. All right, so you have your graphing calculator near you, I hope. If not, take like a second and run and grab your graphing calculator. Everybody got their calculator? Okay, I'm going to assume that's a yes. So what you're going to do is you're going to hit math. And then I'm almost positive this is option 9 after you hit math. But go down and make sure. It will either look like an integral or it will say f in I in t parentheses. hold on 1 second. Okay. Everybody got that? Everybody see that? Everybody get the math 9 FNIMT or the integral sign? You all see that? Okay. Okay. So if yours has an integral sign, all you're going to do is put a 2 in for the lower limit, a 4 in for the upper limit. Type in the function, except you'll use an x instead of a t, and then put a dx at the end, and then hit enter. It should give you an answer. What does that give you?
7.066.
0.6 what?
6.
Okay, and we'll say millions of bushels, because that's what the answer is. Now, did anybody's calculator, when they pushed the FNINT button, come up to just say FNINT parenthesis? If it did, that's okay. I just need to tell you what you need to type in, because you're going to need to know how to do this for the AP test. Everybody's calculator just popped up an integral. Okay, I don't want to hear later that yours didn't do that, that yours didn't give you the integral, that it gave you this, and you don't know how to do it. So everybody's gave you the integral sign, and you just typed it in. Okay, all right, that's our answer then. We're done. Easy enough? Should be, I hope.
Yep.
All right, let's do another one. So here we've got a pump that is connected to a generator, and it's operating at a rate that varies because the generator is powering lots of different things. And so every 5 minutes, we calculated exactly how quickly in gallons per minute it was pumping. And so we want to know how many gallons were pumped in this hour. So we are accumulating a certain amount each hour, or I mean each, every 5 minutes we're accumulating a certain amount of gallons. And so that's going to be like our accumulator function for the last one, where we're accumulating a number of millions of bushels of potatoes per year. Does that make sense or no? Okay. So to accumulate this, we're going to integrate the rate function, which unfortunately we don't have a rate function given to us. We just have a set of data points, but we need to integrate it from 0 to 60, right? And so since we don't actually have an official rate function, what we need to do is we need to approximate this using one of our rules. Which rule do you think we should use to approximate it? Doesn't matter, there's 4 different options. How about the trapezoidal rule? That seems like an easy one because it's got a formula for it. Everybody following, or everybody good?
Yeah.
Okay, so we're going to use the trapezoidal rule to approximate this integral. So that should give us b minus a, 60 minus 0, over n, which is the number of intervals, which is 12, because it's every 5 minutes from 0 to 60, divided by 2. And then we have to just plug in 58, and 2 times 60, and 2 times 65, and so on, all the way up till 2 times 63, and then just 63 at the end. So I'll give you guys a second to figure that out, and then you should be able to tell me how many gallons were pumped during that hour. So I'll let you do that arithmetic. Anybody got a number for that or no? Anybody?
I don't know if it's right, but I got 3,582.5.
Yeah, that's what I
That's
got.
pretty
too.
good.
I didn't know if it was right either.
I mean, if you think about it, it should be pretty close to that, right? It's pumping about 58, 60, 65, 64 gallons per minute. So if you look at those, they're all around 60, right? So it looks like it's pumping about 60 gallons about every minute. And we've done 60 minutes, so that'd be 60 times 60, 3,600, right? So you're pretty close to 3,600. That seems like seems like you're in the right ballpark at least, right?
Yeah, that makes sense.
Yeah, so it's a good answer. Sounds good to me. Any questions on that, anybody? So if we had a function, we would have used the function and integrated, but since we didn't, we used one of our rules to approximate integrals. That make sense to everyone or no?
So like for an unequal interval, we would have to like do the long way, right? We'd have to, like,
You
multiply
would,
everything.
yeah. Yep, you'd have to find each one separately. Hopefully I won't make you do that.
Yeah. it's-
All right, last one. So I'll let you read through it, and then I want to see if you guys can take a minute to sort of set it up on your own. I'm going to give you maybe 3 minutes to try and get it set up, and then we'll sort of talk through it to make sure everybody's on the same page. Sound good? This will be our last one of the day. So 3 minutes, read through it, try and figure out how you want to set it up. Ready? Go. So we're thinking about people in an amusement park, and we're given 3 different pieces of information. One, that the number of people that enter, the rate at which people enter from 0 to 6 is this graph. Second, we're given that the rate at which people leave is L of t. And third, we're given that there are 3,000 people in the park at noon. And so we want to figure out how many people are actually in the park at 6 p.m. So in order to figure out how many people there are, we got to know, first off, the number of people at noon that were already in the park. Then we have to add the number that enter. And then we have to subtract the number that leave. Right? And that's how you get the number at 6, the number that are there, plus the number that enter during the time period, minus the number that leave during the time period. That should be the total number at the end. True? Yes, no, maybe? Yeah.
Yeah.
Okay. Cool. So how many people are there at noon?
3,000.
3,000. So that's an easy one. Then the number that enter ought to be an integral of the rate at which they enter. So that's the integral of E of t dt from 0 to 6. So we'll worry about that in a second. Minus the number that leave, that's the integral from 0 to 6 of L of t, the rate that they leave, function L of t dt. Good? Everybody good with those? Integral of rate they enter is the number that enter. Integral of rate that they leave is the number that leave. Yeah. Okay. Cool. 3,000, like we said, is just 3,000. How many enter between 0 and 6? The integral of E of t, which is, well, graphically, that's just the area underneath the curve. So all we have to do is figure out what's the area underneath this curve from 0 to 6. I can break that up into 3 little sections here. 2 trapezoids and a rectangle. So we just got to find the area of each of the trapezoids, and we got to find the area of a triangle. And so the area of the first trapezoid ought to be base 1, 400, plus base 2, which is 600, that's 1,000, right? Divided by 2 should be 500, times the height of 3 ought to be 1,500. And then this little rectangle has a height of 600 and a width of 1, so that ought to be 600. And this trapezoid has 2 bases, 600 and 500, divided by 2, and then times the height of 2 should give us 1,100. Everybody agree with that?
Yep.
Add those three together, that's 3,200. And then minus whatever this integral is, and then this integral will just pop into our graphing calculator. And what do you get for this integral here?
I got about 2106.
2106 point something probably. Does it round up to 2107 or does it say at 2106?
2106. It's 0.4.
Okay, 0.4. So we'll say 0.4 of the person is left. Somebody was in the process of leaving, but hadn't got half of their body out the door yet. So 2106 people had left. And so all we have to do is put those together, and what do we get as our final answer?
$4,094.
Looks like 4,094 people. Okay. So those are called accumulator functions, or they're like net change functions. And those sorts of problems pop up fairly often on the AP test. So we're going to practice a lot of those during quarter 3, stuff similar to this. Any questions on that or anything else we've done today?
Oh, just wondering, are you going to post more practice for integrals, or just last night's homework was the practice?
I might be able to find a few more I could throw up. I probably won't put a ton up, but yeah, I'll put a couple up sometime this afternoon. I don't have anything made right this minute. I got to help Kristen with his problems with polar area before I can even do that too. So yeah, I'll put something up.
All right, thank you.
Other questions?